What if I told you the most important technology behind modern artificial intelligence wasn't invented for intelligence? It wasn't designed to think, it wasn't built to learn, and it definitely wasn't meant to change the world. At least our world. It was built to play video games. This is the story of how graphic cards, or GPUs, went from making video games look better to powering artificial intelligence, massive data centers, and entire industries. Not because anyone actually planned it, but because AI spent decades waiting for one machine that could finally run it. But for all this, we have to go back over 70 years. Long before GPUs, the idea of artificial intelligence already existed. You see, back in the 1940s and 50s, computers filled rooms. They weren't our compact desktops or laptops. They were huge. They overheated, they barely worked, but one person wasn't really focused on what computers could do, only on what they might become. This is Alan Turing, a mathematician and codebreaker who helped end World War II. And he asked a strange question. Can a machine learn? Not calculate, not follow instructions, but change its behavior based on experience. And that idea was way ahead of its time. And computers simply weren't powerful enough to even try. AI didn't fail because the idea was wrong, it failed because the hardware just wasn't ready for it. And then a few years later, that idea became a real machine. This is Frank Rosenblatt. Sorry if I'm saying that wrong. He's a psychologist who tried to copy how learning works in the brain. And he noticed something that was really important. Our brains don't follow step-by-step rules. They learn by adjusting connections. So in the late 1950s, he built the perceptron. Information went in and an answer would come out. And when the answer was wrong, the connections would adjust slightly. No rules, no instructions, just learning. And for a moment, this is when people thought intelligence was solved. But it wasn't quite there. The perceptron can only handle very simple problems. It couldn't learn layers, and mathematicians proved that there were many things it could never learn at all. So funding disappeared, people moved on, and AI went into its first long winter. But one key idea survived from this. Maybe intelligence doesn't come from rules. Maybe it comes from adjustment. That idea didn't disappear, it grew. Researchers realized the problem wasn't learning, it was scale. One learning layer wasn't enough, so they started stacking them. And that's how the neural network was born. A neural network isn't a brain, it's a learning machine that works like this. It takes something in, a picture, a sound, or words, and it turns that into numbers. Those numbers move through a layer of connections and an answer comes out. And then that answer is checked against reality. And every connection adjusts slightly. Then it does it again and again and again, millions of times. Learning doesn't come from understanding. It comes from making mistakes and correcting them. This made sense because researchers already knew something important. You can't write rules for recognizing faces. You can't write rules for understanding language. And you can't even write rules for intelligence. But you can't let a machine learn its rules and create its own if it gets enough practice. But there was just one problem. You see, neural networks needed to repeat the same math over and over and over again. The same calculations across thousands, then millions of connections. But the processors running this idea, they were CPUs. And CPUs were built for a very different kind of work. A CPU is like a smart manager. It looks at a problem and it makes a decision, then chooses what to do next. It's like, if this happens, do that. And if not, do something else. It's just a branch. And that's perfect for operating systems like apps and logic-heavy programs. And neural networks don't really work like that. They don't make decisions step by step. They take one simple operation and apply it everywhere at the same time. They don't branch, they flood. And a GPU like this is built for flooding. Instead of deciding on what to do next, it takes one instruction and then runs it thousands of times in parallel. The same math, the same operation, everywhere. And that difference between branching versus flooding is why CPUs struggled with AI for decades, and why GPUs didn't. They weren't just good at math, they were good at moving huge amounts of data at the same time, which is exactly what neural networks needed. And this is where the whole story takes a turn. Fast forward a few years, and this is Geoffrey Hinton
to tell us about the developments that led to this year's Nobel Prize in Physics.
Who was a researcher who kept working on neural networks even when most people gave up. He believed in one thing very strongly. The math behind AI works, but our hardware didn't. And lucky enough, at the same time, video games were becoming more realistic. Games needed lighting, shadow, and physics all at once. And to make that happen, companies built a new kind of chip, the GPU. And unlike CPUs, GPUs don't need to make decisions. They do the same simple calculations thousands of times at the same time. They aren't exactly smarter than CPUs, but they're much smarter. That turned out to be exactly what neural networks needed. And that's when NVIDIA released something that changed everything. CUDA. Compute Unified Device Architecture. And CUDA let programmers use GPUs for more than just graphics. Instead of drawing pixels, GPUs could now multiply numbers, thousands of them, all at once. And this is when Hinton students rewrote the neural network code to run on consumer-grade GPUs, specifically the NVIDIA GTX 280 graphics cards, which were released in 2008. These weren't special machines, they were just consumer-grade hardware, but training times collapsed. What used to take weeks now took days, then hours. For the first time, deep learning actually worked, but it still needed to prove itself. Not a demo, not a lab experiment, a real test. And that test was ImageNet. ImageNet was a massive collection of more than 1 million real-world images. And these were not clean pictures, not perfect examples, just a ton of messy photos, bad lighting, hidden objects, and crowded scenes. It was designed to reflect the real world. And every approach to AI before it pretty much failed. Then one of Hinton's students created AlexNet and entered the competition in 2012. And it was trained on just 2 GPUs, the GTX 580s. And it didn't just win, it crushed everything else. The improvement was so large it ended the argument overnight. Neural networks worked, and GPUs were the reason. At the same time, something else was happening. Crypto was booming, and it discovered the same thing AI had. GPUs were perfect for repeating simple math non-stop. So stores sold out, prices shot up, and warehouses filled with GPUs running all day and night. Now this isn't a crypto story, what mattered was the lesson. GPUs could run continuously at massive scale with huge power and cooling demands. And our beloved graphics cards wasn't a consumer toy anymore. It was becoming infrastructure. And from here, everything sped up. Neural networks grew larger and data sets exploded. Models stopped fitting onto one computer, so AI moved into clusters, then buildings, then massive data centers. And as these facilities got bigger, researchers noticed something important. Bigger models just worked better. More data helped, but more GPUs improved the results. And this wasn't luck, it was just math. AI progressed now depending on one thing. How much computing power could you afford? Then at some point, AI learned language. Earlier systems read one word at a time, but newer models could look at all the words together and understand how they relate. And that made AI good at writing, explaining, and having conversations. But learning language this way takes enormous practice. And that practice meant doing the same math trillions of times. Training these models required thousands of GPUs running non-stop for weeks or months, and only the largest companies could actually afford that. And almost overnight, work changed. Writing drafts, summarizing documents, writing code, creating images, and analyzing data. Tasks that once took hours now took seconds. Not because humans got smarter, but because GPUs were doing the repetition for us. And suddenly one person could do the work of 5 or 10 people. Modern AI data centers aren't server rooms. They're factories. They cover massive areas and draw city-level power. And on top of that, they cost billions to build. AI is no longer just software. It's physical. Building AI now looks less like writing software and more like running a factory. So now you know, AI didn't suddenly appear. This idea existed in the 1950s. The math already worked decades ago. What was missing was the right machine. And that machine wasn't the CPU, it was the GPU. Built for games, turned into a math engine, and then scaled into data centers. Every modern AI system, they exist because GPUs became big enough to run at scale. And the story isn't even over. GPUs didn't become AI because they were perfect, they became artificial intelligence because they were the first machine good enough. So whatever comes next, we'll have to beat them at the same thing. And thanks for watching, and I'll catch you guys next time. Ciao.